We're going to go ahead and get started with Unit 8 today. So we're talking about sections 8.1 through 8.3 today. All right, we're going to start just with some basic definitions of acids and bases, what they are, and also pH. You guys have heard of pH, I'm sure, before as a measurement of the acidity of a substance. So just a quick reminder that the pH scale goes from 0 to 14. A pH of 7 represents a neutral substance, and anything below 7 represents an acidic substance. Anything above 7 represents a base. So when we calculate our pH values, we're basically calculating the concentration of hydrogen ions or hydronium ions. So let's remember some things about acids. Let's go down here to these equations first. So when we talk about acids are things that produce hydrogen ions. If I have HF, which is hydrofluoric acid, and I put it in water, this hydrogen comes over here, joins the water molecule, forms this H3O+. This is called hydronium, and it's the concentration of hydronium ions that determines the pH of a substance. So we can also write this equation like you see above. Instead of showing water in our equation, we can take water out of the equation. If we show that, we show how HF breaks apart into hydrogen and fluoride ions. So calculating the pH can be calculated just by taking the concentration of our hydronium ion, which can also be written as the concentration of hydrogen ions, and we can just negative log that number will give us pH. pOH is going to be like measuring the basicity of a solution. We're just going to negative log that OH concentration. A couple of other important equations that we have here. Let's talk about water for a second. So this term autoionization, ionization just means a compound breaking apart into ions, right? So auto just means that it does it all by itself. So if we remember H2O as like HOH, where we have a hydrogen ion and a hydroxide ion, there's a small percentage of those hydrogen and hydroxide ions that will break apart in water on their own. And so that ionization equation shows our water breaking apart into hydrogen and hydroxide. So now we have another K value right here. Remember, this is the same way we do K for KC we've done KP, we've done KSP, now we have KW. It's still products over reactants. So my products in this autoionization equation are hydrogen, you don't have to rewrite this, and hydroxide. And I'm not going to include my reactants because it's a liquid, and we only include aqueous substances and gaseous substances in our K expressions. So this is going to be my K expression for the autoionization of water, and that has a constant value, which is 1 times 10 to the negative 14. The reason why that's important is because we're going to be dealing with acid and base solutions where maybe we know the concentration of hydrogen and we need to find the concentration of hydroxide, or the other way around, and we can use this equation to do that. Another equation we can use is our pH and pOH. When we add those together is going to give us 14. So there will be times where we're able to calculate pOH, and so we can use this equation to work backwards and solve for the pH value of the solution that we're looking for. You guys have 2 boxes at the bottom of your page in this section of your notes, one for strong acids and one for strong bases. So we have this from Unit 4, I think. You guys memorized your strong acids and strong bases. Also going to be important again for this unit, so let's remember what those things are. There are 6 strong acids that you need to have memorized. Those are HCl, HBr, HI, H2SO4, HNO3, nitric acid, and then perchloric acid, HClO4. That's going to be important when we start to calculate our pH values, because the way our strong acids and our weak acids behave is going to be different. For our strong bases, we have our group 1 hydroxides, and most of our group 2 hydroxides, that would be beryllium, magnesium, calcium hydroxides. Some important concepts when we're talking about acids and bases have to do with understanding what it means for something to be a strong acid and what it means for something to be a strong base. So when we're talking about strong acids or strong bases, those are going to be the acids and bases that completely ionize in water, completely dissociate. The differences with acids, of course, we're producing hydronium or H plus ions. With strong bases, we're producing hydroxide ions. The important thing to understand about that is if you know the concentration of the acid, then you also know the concentration of the hydronium ion. So for example, if you have HCl and you have a 1 molar concentration of HCl, when that breaks apart into hydrogen and chloride ions, that concentration of hydrogen is going to be 1 molar, concentration of chloride is also going to be 1 molar. So when we're calculating the pH, we would negative log that hydrogen ion concentration would just be 1. Same thing with hydroxide. Okay, so let's go ahead and take a look at some pH calculation examples. Our first example I kind of touched on a little bit already. First thing you need to do is when you see the formula for your acid, you need to think about, is this a strong or weak acid? So this is nitric acid, this is strong. And calculating the pH of strong acids and bases is much easier than calculating the pH of weak acids because we know the concentration. Remember, if I know the concentration of a strong acid, that is also going to be the concentration of my hydrogen ions. So all I have to do here, if I know it's a strong acid and there's only 1 hydrogen there, my pH is going to be the negative log of that number, which is 0.1, which gives me a pH of 1, which is acidic. We know that anything less than 7 is an acidic solution. Let's go ahead and take a look at these 2 examples. I've got sodium hydroxide, I've got calcium hydroxide. So for sodium hydroxide, when that breaks apart, we get sodium, we get hydroxide. So since we get 1 hydroxide and that mole ratio is 1 to 1, then I can go ahead and negative log that concentration of 0.25. When I negative log 0.25, that's going to equal 0.60. However, when you negative log the hydroxide ion concentration, what that's going to give you is the pOH. So anytime you're dealing with a base, you have one extra step at the end, and that is to calculate the pH, you have to take 14 and subtract that pOH value, and that's going to give you your pH. And it's the pH value that we actually look at to determine if something is acidic or basic. So that was for sodium hydroxide. Let's take a look at calcium hydroxide. When calcium hydroxide ionizes, I get 1 calcium, but I get 2 hydroxides this time. So if you get more than 1 of hydrogen or hydroxide, you do have to pay attention to that. So we're going to deal with the same concentration here. So if this is 0.25, then because the mole ratio is 1 to 1 for calcium, this also has a concentration of 0.25, but my hydroxide has a concentration that is double that. So my concentration of hydroxide is actually 0.5. So the number that you want to negative log is the number that goes with hydroxide. So my pOH value is going to be the negative log of 0.5. When I negative log that number, that gives me 0.3. To calculate the pH, I have to subtract that number from 14. So my pH is 13.7, which is a very basic pH for a solution. Okay, we also need to know what to do when we mix 2 solutions together. So in this case, I've got 54 milliliters of this concentration of nitric acid. I have 25 milliliters of this concentration of hydrochloric acid. So what is the pH? Now, remembering that pH is the negative log of my hydrogen ion concentration, I need to figure out what the total hydrogen ion concentration is when these two things are mixed together. Remember, anytime we mix things together, just like we did with, what did we do this with? Solubility. Whenever we mix two solutions together, we have to figure out what the new molarity is, because if I have 54 milliliters of this and 25 milliliters of this, when I mix them together, they have a volume of 79 milliliters. And changing the volume also changes the concentration. So what I want to do is I want to, for nitric acid, I want to go ahead and do M1V1 equals M2V2 to figure out that new concentration of nitric acid when the two solutions are mixed together. And then I have to do the same thing with HCl. All right, so plugging in my initial molarity, I have 0.00125. My initial volume here is 54. M2 and then times 79. So my final molarity there is going to be 8.54 times 10 to the negative fourth. My initial molarity of HCl is 0.025. That initial volume is 25. Solving for M2, final volume 79. That M2 value is 0.0079. Now, that's going to give me the hydrogen ion concentration that comes from nitric acid. That's going to give me the hydrogen ion concentration that comes from HCl. I need to add those numbers together. When I do, that's going to give me my total hydrogen ion concentration, which is 0.00877. So then to calculate my pH value, I can negative log that number, which gives me a pH of 2.06. Okay, anytime you mix solutions together, you have to do this M1V1 equals M2V2 step to get your new molarity values before you can plug them in, just like we've done before. Okay, so we're going to go ahead and take a look at how we're going to calculate pH values for weak acids, which is going to be a little bit different because weak acids only partially ionize. So you're not going to have, whatever the concentration is of your original acid, that's not going to be the concentration of your hydrogen or your hydronium ion. It's going to be much less than that. So this equation right here, this is kind of the general format for the ionization of a weak acid. So when it reacts with water, you'll get hydronium ion, and you'll get A minus just represents the anion that is attached to your hydrogen ion. So for example, if I had HF, HA is just the general formula of a weak acid. An example of that would be HF plus water, and then I get H3O plus. And then my anion that's left over when the hydrogen leaves is going to be the fluoride ion. So you'll see sometimes just the generic formula written the way I have in your notes. This is a specific example of that. So in order to calculate the pH of weak acids, we're going to use their Ka values. So now we have Kc, Kp, Ksp, Kw, and now we have Ka. Ka is just going to be that ratio of products to reactants, products on the top, reactants on the bottom, of a weak acid. So I've got my hydrogen and my anion concentrations on the top, and my weak acid concentration on the bottom, and then of course we leave out water because it's a liquid. This equation, we're going to get back to this equation a little bit later on. All right, let's take a look at this example. We are going to calculate the pH of a 0.25 molar solution of HCN. HCN is a weak acid. Now, acid-base pHs, for weak acids, weak bases, you guys are going to be using ice tables still. I told you guys we were going to be using ice tables for a little while now. So you have to start out by writing out your equation for the ionization of your acid. So we can leave water out of the equation because we know we don't need it for our K expression. So HCN is going to break apart, but it's kind of like those KSP problems where Not all of it breaks apart, only some of it breaks apart, and we have to figure out what amount does. And they give you the Ka value. So I'm going to go ahead and start with my zeros over here on the product side. And the initial concentration was 0.25 of the HCN. I'm going to end up with plus X here, and minus X here. Now, notice that X is going to equal my hydrogen ion concentration. And if I'm calculating pH, pH is the negative log of that hydrogen ion concentration. So if I can solve for X, then I can just plug that in there to calculate my pH value. Okay, so my Ka expression is going to be my hydrogen plus my cyanide, that's what Cn minus is, and then over HCN here. My Ka value is given to me, it's 4.9 times 10 to the negative 10, and I'm going to have X times X on the top, so that's going to be X squared. Now for this expression right here, also remember that when my K value is really small, then my X value is really small, so I don't need to include that. So I can just put 0.25 down here, and that's going to make the math a lot easier for me to do. So from there, X is going to equal 1.11 times 10 to the negative 5th. And I know that X, remember, X is my hydrogen ion concentration. So to calculate my pH, I just need to negative log that number. And that's going to give me a pH value of 4.96. You should always double check and make sure that your answer makes sense. We're dealing with HCN, which is acidic, so my pH value should be less than 7, which it is. Let's take a look at a problem where we're going to mix two acids together. So when you mix two acids together, you need to look at which acids you have. I've got nitric acid and nitrous acid. Nitrous is weak. Nitric acid is strong. When you have a strong and a weak acid mixed together, then it's really the strong acid that's going to dominate the pH value, because you're going to have 100% ionization here, and weak acids have like, I don't know, 1 to 3% ionization. It's really, really small, so you're not going to have very many hydrogen ions dissociating or ionizing from your nitrous acid. So really, I don't have to pay attention to this except for the volume, because for HNO3, I have 25 milliliters of it and 250 milliliters of the nitric acid being added to it. So together I have 275 milliliters. So remember, just like we've talked about already today, anytime you mix two solutions together, you need to use this equation to calculate your new molarity. Once you have that new molarity, that's going to be the hydrogen ion concentration that you want to negative log to solve for the pH. So I've got 0.25 molar for nitric acid, 25 milliliters of that. I want to solve for M2, final volume 275. That gives me my final volume when those two solutions are mixed together is 0.0227. Okay, negative logging that number is going to give me the pH. And that pH value is going to be 1.64. Let's go ahead and move on and talk about bases. So bases, remember those strong bases produce hydroxide ions, but even weak bases will react with water. We talked about this back in Unit 4, but just a reminder, those weak bases will produce hydroxide because of the way they react with water. So this right here is just kind of my general formula for a base reacting with water. One of those hydrogens comes over here, attaches to my base, and leaves me with hydroxide. So for example, really common example. NH3 is ammonia plus HOH, which is water. Any weak acid base should have double arrows. I should have a double arrow there. That hydrogen is going to come over there, form NH4 plus, and then have hydroxide left over. Weak bases only partially ionize, and so that hydroxide ion concentration is going to be less than the initial concentration of the base, just like with our acids. And most of them remain unionized and remain together as just the base molecule. And so now I have my Kb values, which show the ratio of products to reactants based on the equation for the ionization of our base. So in this example, we're going to go ahead and calculate the pH of a basic solution, NH3. Always need to start out with our equation. With our basic equations, we are going to show water. With our acidic equations, we don't have to because we can just show them breaking apart. With our base equations, we do because it shows us that that hydrogen breaks off of the water to form NH4 plus and leaves us with hydroxide left over. So just like we used an ice table for our weak acids, we're going to use ice tables for our weak base also. With my initial concentration is 0.25. Water I don't include in my ice table. I have 0 plus x is x, 0 plus x is x minus x here. And since x is so small, I can disregard that in my K expression. With weak bases, they're going to give you Kb values instead of Ka values. So I'm going to have 1.8 times 10 to the negative fifth. My products, x times x squared over 0.25. The difference with this problem is that when I calculate x, I'm calculating hydroxide, not hydrogen. So when I solve for that number, and it's 0.00212, when I negative log that number, and it gives me 2.67, that's my pOH value. So you're not finished yet. Anytime you are calculating the pH of a weak base, you have an extra step at the end where you have to subtract it from 14. So 14 minus 2.67 will give me a pH of 11.3. Again, double check your answer. So I'm dealing with a basic solution, so my pH needs to be greater than 7. So it makes sense that we can't stop here. We have to subtract from 14 to get that pH in the basic range. The last thing that we need to talk about today is percent ionization, and this is going to be for everything weak. So for our strong acids and bases, the percent ionization is always going to be 100%, basically. All of the strong acids, strong base molecules break apart. But for weak acids, weak bases, only some of them break apart. And so we need to be able to calculate what that percentage is. So we're going to take a look at this. This is benzoic acid. So in this question, they actually didn't even give me the formula for benzoic acid. So usually they will. If they do not give you the formula of benzoic acid, we can just use the generic formula HA, because I know that there's going to be hydrogen in the front. I know that there's going to be some anion attached to it, whatever that is that makes it benzoic acid. That actually makes it easier because, let me show you, benzoic acid is actually HC7H5O2. So I have my hydrogen, and then this whole thing is my anion. So you can choose to write that all out if you want to. If you don't want to, you can kind of use your general formulas here for HA as my weak acid and A minus as my anion. We want to calculate the percent ionization for 0.5 molar. So starting with 0.5, I'm going to go ahead and solve for X again. Disregarding with my weak acids, we're going to be dealing with problems where you can disregard this X because it's going to be so small. They did give me the Ka value, so 6.5 times 10 to the negative fifth will be X squared over 0.5. X is going to be my hydrogen ion concentration. That's going to be a value of 0.0057. Now, when you are calculating your percent ionization, you want to figure out if 0.5 is what I started with, how much of it actually broke apart, which is going to be my X value or my H plus ionization. So you guys can see in this equation up top that I'm going to take my hydrogen or my hydronium ion concentration, same thing, and I'm going to divide that by my initial concentration, what I started out with. It's just like calculating percent of anything, how much of it broke apart compared to how much I started with. So I'm going to have 0.0057. That's going to go over my initial concentration, and to turn it back into a percentage, I'm going to multiply by 100. That's going to give me a percent ionization of 1.14%. So what that means is out of all of the HA molecules or all of the benzoic acid molecules, only 1.14% of them are actually going to break apart. The rest of them are going to all stay together. So when you guys come to class next time, we're going to do lots of pH calculations, percent ionization calculations. So make sure that you bring your notes with you, and I will see you guys in class.